Our galaxy hides worlds stranger than any fiction. We are about to embark on the ultimate cosmic treasure hunt, counting down the 30 most promising planets where alien life could be thriving right now. By the end, you will have a map to the most astonishing potential homes for life in our stellar neighborhood. We will visit planets with global oceans deeper than our tallest mountains, and super-Earths where gravity itself is a crushing mystery. What does it truly take for a world to become a cradle for life? The answer is far more diverse and surprising than we ever dreamed. Are you ready to meet our potential cosmic neighbors? Our journey begins right next door, cosmically speaking. Just over 4 light-years away, a world called Proxima Centauri b orbits the closest star to our Sun, a small red dwarf named Proxima Centauri. This discovery shattered a long-held assumption that life-bearing planets were likely rare. Here was a rocky world with a mass just a bit larger than Earth's, sitting snugly within its star's habitable zone. That is the orbital sweet spot where temperatures could allow for liquid water to exist on the surface. Picture a planet where the sun in the sky is a deep, perpetual crimson, casting long shadows across a potentially alien landscape. The sheer proximity of this world is its most revolutionary feature. 4 light-years is still an unimaginable distance for human travel, but for our telescopes and future probes, it is practically within shouting distance. This closeness means we can study it in detail, unlike any other exoplanet, searching for the faint chemical fingerprints of an atmosphere or even signs of biological activity. Yet, life on such a world faces a formidable challenge. Red dwarf stars like Proxima Centauri are notoriously temperamental. They frequently erupt with violent stellar flares, blasting their orbiting planets with intense radiation and charged particles. A flare from Proxima could be hundreds of times more powerful than anything our Sun produces. For life to survive there, it would need a robust magnetic field to deflect the radiation, or perhaps a thick atmosphere to shield its surface. Some scientists hold out hope that Proxima b might possess just that, a thin but tenacious blanket of gases holding warmth and protection against the stellar storms. This creates a fascinating paradox, a potentially Earth-like world locked in a deadly dance with its furious parent star. Is it a irradiated wasteland or a sheltered oasis clinging to existence in the cosmic dark? The answer may lie in that whisper-thin atmosphere, a secret we are only now learning how to detect from across the interstellar void. But the story of red dwarfs and their hidden worlds only grows more astonishing. Just 39 light-years away, a star barely larger than Jupiter holds a secret that rewrote the rules of planetary systems. TRAPPIST-1, an ultra-cool dwarf star, is home to not 1 or 2, but 7 known rocky planets, a miniature solar system packed into a space smaller than Mercury's orbit around our Sun. Among this celestial family, one world stands out as a prime candidate for life, TRAPPIST-1e. This planet is almost a perfect twin to Earth in size and density, a solid, rocky world with the right ingredients for a surface. Crucially, it sits squarely in the middle of its star's habitable zone, receiving just the right amount of starlight to potentially host liquid water. Yet, its proximity to such a faint star comes with a profound consequence. TRAPPIST-1e is almost certainly tidally locked. This means one side of the planet faces its sun in perpetual, blazing daylight, while the other is plunged into eternal, frozen night. For decades, scientists thought such a world would be inhospitable, a planet of extremes with a scorching desert on one hemisphere and a global glacier on the other. But the magic might happen in between, along the razor-thin boundary known as the Terminator line. Picture a perpetual twilight zone encircling the entire planet, where the searing heat of the day side gradually gives way to the deep cold of the night. Along this narrow band, temperatures could be just right for liquid water to pool and flow. Rivers might cascade from the icy night side, only to evaporate as they reach the day side's edge, creating a dynamic, stable zone for chemistry to thrive. It is a world of permanent sunrise and sunset, a ring of potential habitability clinging to the edge of light and dark. Right now, the most powerful space telescope ever built, the James Webb Space Telescope, is turning its golden eye toward this extraordinary system. Its mission is to sniff out the atmosphere of TRAPPIST-1e, analyzing the starlight that filters through any gases surrounding the planet. A detection of water vapor, methane, or even oxygen would send shockwaves through the scientific community, transforming this distant rock from a promising candidate into our best bet for a world that actually hosts life. The answer is hanging in the thin air of a twilight world, and we are finally listening. The discovery of Kepler 186f was a moment that changed astronomy forever. Before this world was found, we knew of gas giants and strange, scorched worlds, but the question remained, were there other Earths out there? In 2014, the Kepler Space Telescope gave us a definitive answer. Orbiting a cool, red dwarf star about 500 light-years away, Kepler 186f was the first rocky planet, nearly identical in size to our own, found orbiting comfortably within the habitable zone of another sun. It was proof planets like ours were not a cosmic fluke, they were a common feature of the galaxy. This distant point of light, smaller than a pixel in even our most powerful telescopes, became a symbol of profound possibility. Its star is smaller and cooler than our sun, so its habitable zone is much closer in. A year on Kepler 186f, one full orbit, lasts only about 130 Earth days. Yet, because it receives a similar intensity of starlight as Mars does from our sun, its potential climate hangs in a delicate balance. Scientists believe it is likely a rocky world, perhaps with a solid surface where water could, in theory, pool. The longer orbital period compared to many other red dwarf planets suggests a more gradual dance with its star, which could allow for a more stable climate over eons. Imagine seasons that are subtle and drawn out, not defined by a drastic tilt like Earth, but by the slow, steady pulse of its distant crimson sun. The light that reaches its surface would be tinged with red, bathing any potential landscapes in a perpetual sunset-like glow. While we do not yet know if it has an atmosphere or oceans, Kepler 186f's true legacy is not about the specifics of its environment. Its legacy is that it opened the door. It showed us that the building blocks for an Earth, a world of rock and potential liquid water in the right place, are scattered throughout the cosmos. It turned the question from if to how many. After its discovery, the hunt accelerated and the list of hopeful worlds began to grow. Kepler 452b is the closest thing we have found to a mirror of our own world. Orbiting a star almost identical to our Sun, and at nearly the same orbital distance, this planet experiences a year just 20 days longer than ours. The sunlight bathing its skies would feel familiar, a warm, yellow-white glow rather than the deep crimson of red dwarf systems. This is not just another candidate, this is Earth's older, bigger cousin. Its discovery answered a question we had been asking for millennia. Are there other Earths around other suns? The data says yes, but this cousin is a formidable one, a super-Earth with a radius about 60% larger than our home. That extra bulk translates to a surface gravity that could be more than twice as strong as what we experience. Picture a world where everything feels heavier, where mountains might be pressed down into broader, lower hills under the constant, immense pull. The very air could be thicker, creating a denser atmosphere that would scatter light differently, perhaps painting the sky in deeper shades of blue or perpetual, hazy twilight. That thick atmosphere could be a blessing for life, acting as a global insulator to maintain stable temperatures and a powerful shield against cosmic radiation. It might also fuel a world of intense and active geology, with more heat trapped in its interior driving relentless volcanic activity. Continents on such a planet could be constantly reshaped by titanic forces, creating a dynamic, ever-changing landscape. Could life arise and thrive under such conditions? Biology is remarkably adaptable. Perhaps forests on this super-Earth would evolve with stronger, denser wood to support trees against the powerful gravity. Animals might develop more robust skeletal structures, moving with a deliberate, powerful grace. Flying could be a far greater challenge in a dense atmosphere, but not impossible, potentially leading to creatures with immense wingspans or novel forms of locomotion. Kepler 452b presents a profound thought experiment. It shows us that the template for a living world is not a single, fragile set of conditions. It can be scaled up, made more massive and more intense, and the spark of life might still find a way to catch and flourish under a heavier sun. While some super-Earths are scaled-up versions of our world, others represent something entirely different. Deep in the constellation Cetus, a planet named LHS 1140b presents astronomers with a tantalizing puzzle. Orbiting a remarkably calm and quiet red dwarf star about 48 light-years away, this world sits perfectly within the habitable zone. Its star's stable nature is a gift, offering a far more peaceful environment than the violent flares of Proxima Centauri, which means any potential atmosphere or ocean is not being constantly stripped away by stellar tantrums. This makes it one of the most promising targets we have for peering into an alien sky. But what would we see there? The planet's density measurements leave us with two equally fascinating possibilities. The first is that LHS 1140b is a massive, dense ball of rock and metal, a super-Earth with a colossal iron core that generates a powerful magnetic field, a perfect shield for a developing biosphere. The second, and perhaps more captivating idea, is that this world is not predominantly rock at all, but water. It could be a global ocean planet, a water world with no land in sight. Imagine an entire planet where the surface is a single, endless sea, stretching from pole to pole, hundreds of miles deep. The pressure at the bottom of such an abyss would be crushing, creating exotic forms of ice not from cold but from sheer force, a solid floor of hot ice beneath a dark, watery universe. In such an environment, life would be exclusively aquatic, but not as we know it. Without shores or continents, evolution would follow a radically different path. Complex ecosystems could thrive at different depths, from sunlit surface waters teeming with floating organisms to the dark, high-pressure realms near the strange, hot ice bottom, where life might draw energy from hydrothermal vents or chemical reactions in the water itself. Intelligent life here might never conceive of a world with land, their entire cosmos defined by fluid dynamics, pressure gradients, and the faint light filtering down from above. The James Webb Space Telescope is poised to solve this mystery by analyzing the starlight that passes through this planet's atmosphere, if it has one. A detection of water vapor would be a monumental clue pointing strongly toward the ocean world scenario. LHS 1140b reminds us that a habitable world does not need to look like Earth. It could be a planet of profound, silent depth, a global aquarium waiting for its secrets to rise to the surface. But what if the most Earth-like world we have found is not around a young, sun-like star, but one of the oldest in our galactic neighborhood, 12 light-years away, circling a faint red dwarf named Tidal star, is a planet that scores higher on the Earth Similarity Index than any other known world. Tidal star B is a rocky planet, only slightly more massive than Earth, and it orbits snugly within its star's habitable zone. The numbers are astonishingly familiar, suggesting that if this planet has even a thin Earth-like atmosphere, its average surface temperature could be remarkably temperate, perhaps even hovering around the freezing point of water. This is not a world of crushing gravity or eternal twilight, but one that on paper could feel strangely like home. The starlight reaching it would be a dim, ruddy glow, but the potential for liquid water is a powerful beacon in the search for life. The true wonder, however, lies not just in its position, but in its profound age. Tidal's star is ancient, a stellar relic that has been burning quietly for at least 8 billion years. That is nearly twice the age of our own solar system. This single fact opens a chasm of possibility. If life did emerge on Tidal star B, it has had an unimaginable head start. While life on Earth has taken 4.5 billion years to evolve from single-celled organisms to a civilization that builds telescopes, any biology on that distant world has had almost twice that time to develop. What could evolution accomplish with 8 billion extra years of trial and error? Imagine a biosphere so mature and complex it makes Earth's rainforests look like a barren desert. Intelligence that could be so advanced that our own technology might seem like child's play, or perhaps life has transcended a biological form altogether, existing as patterns of energy or information woven into the fabric of the planet itself. The silence from this nearby, promising world is both eerie and telling. Its star is stable and quiet, offering a peaceful environment for eons, so where is everyone? This is the heart of the Fermi paradox, the question of why we see no evidence of such ancient civilizations. Perhaps life is incredibly rare, and Tidal star B, for all its promise, is a beautiful, empty garden. Or maybe intelligence inevitably turns inward or finds ways to exist that are utterly invisible to our young, probing instruments. This planet is a testament to deep time, a reminder that the universe was building potential homes for life long before our sun even ignited. Yet the story of this ancient star holds another secret. Orbiting alongside its promising sibling is Tidal star C, a world that shares the same venerable neighborhood but endures a very different climate. While both planets reside within their star's broad habitable zone, this second world sits farther out, receiving only about 60% of the stellar energy that its counterpart does. This likely makes it a much colder place, a frozen super-Earth where any water on the surface would be locked in vast global ice sheets. At first glance, that seems to diminish its prospects, but its existence alongside a more temperate world is a revelation. Finding two rocky planets orbiting comfortably within the same star's habitable zone is a rare and precious discovery. It mirrors our own solar system's arrangement, where both Earth and Mars for a time fell within the Sun's life-giving zone. This twin-planet configuration dramatically increases the odds that at least one of them could develop the conditions for life. It is like buying two lottery tickets instead of one, where the grand prize is a living world. But there is an even more intriguing possibility, a cosmic mechanism that could spread life between them. Scientists call this concept panspermia, the idea that life, or its fundamental building blocks, can hitch a ride on rocks blasted into space by asteroid impacts. In a system like Tidal's, where two potentially habitable worlds orbit so close together, this becomes a tangible scenario. Picture a colossal impact on the warmer Tidal star B, launching fragments of its crust and any hardy microorganisms within them out into space. Over thousands of years, some of those rocky fragments could drift across the system and eventually fall onto the frozen surface of Tidal star C. If that icy shell hides a subsurface ocean warmed by the planet's internal heat, those microbial stowaways could find a new home in the dark, watery depths. Life, having arisen on one world, could have seeded the other, transforming a frozen wasteland into a second outpost of biology. This means that in this ancient, quiet system, we might not be looking at one chance for life, but at an interconnected biological network. The two worlds could share a common ancestry, a family of organisms separated by space but united by a violent, creative event billions of years in the past. Gravity is not the only force that can shape a living world. JWST orbits in a stellar ballet more complex than any we have yet encountered. This super-Earth, nearly 4 times the mass of our own planet, circles a red dwarf star that is itself part of a triple star system. From the surface of this distant world, the sky would be a perpetual celestial spectacle. Its primary sun, a dim red orb, would dominate the daytime sky. but hanging in that same heavens, often visible even during the day, would be two other suns, a pair of orange and red dwarfs locked in their own distant embrace, casting a soft additional glow. They would appear not as mere points of light, but as small, distinct disks, forever changing their positions in a slow, majestic dance. This creates an environment of profound and beautiful chaos. The planet's day-night cycle would be dictated by its orbit around its primary star, but the combined light from the other two suns would mean true darkness might be a rare event. There would be periods of multiple sunrises and sunsets, times when the landscape is illuminated by two or even three different sources of light, casting long, intersecting shadows. For life, this cosmic arrangement offers both unique challenges and spectacular opportunities. The constant, varied illumination could drive incredibly efficient photosynthesis, allowing plants or their alien equivalents to harvest energy across a broader spectrum of light. Entire ecosystems might synchronize their activities not to a simple day and night, but to the complex rhythms of the three suns, with dormant periods only when all three have set in a rare celestial alignment. Yet, the gravitational tugs from the companion stars could also make the planet's orbit less stable over immense timescales, potentially nudging it in and out of the habitable zone. For life to persist here, it would need to be resilient, capable of surviving through climatic shifts driven by these subtle gravitational nodes. The discovery of JJ667cc was a landmark because it proved that planets can form and survive in these complex, multi-star environments, once thought too chaotic for stable orbits. It expands the real estate for potential life dramatically, suggesting that even in the crowded gravitational neighborhoods of multiple stars, quiet, rocky worlds can find a home. This is a planet where the sky itself tells a story of cosmic connection, a world illuminated not by one sun, but by a family of them. A world like K218b was never supposed to be on this list. Orbiting a cool dwarf star about 120 light-years away, this planet is not a rocky super-Earth, but a mini-Neptune, a class of world completely alien to our own experience. It is a giant with a radius over twice that of Earth, enveloped in a thick, deep atmosphere of hydrogen and helium. For years, we assumed such worlds were simply gassy, featureless balls, utterly inhospitable to life as we know it. That assumption was shattered when the Hubble Space Telescope, and later the James Webb, peered into its skies and found the unmistakable spectral signature of water vapor. This single discovery rewrote the rules of the search for life. It proved that habitable conditions are not exclusive to rocky planets. They can exist in the most unexpected places, in the skies and on the surfaces of worlds we had previously written off. The environment on K218b would be unlike anything on Earth. Its thick hydrogen atmosphere creates a crushing greenhouse effect, trapping immense heat. While its outer cloud tops might be frigid, the pressure and temperature increase dramatically as you descend. Somewhere deep below those clouds, scientists believe there could be a critical boundary where the pressure is so intense that water cannot exist as a gas anymore, but is forced into a liquid state. This suggests the possibility of a global ocean, but not a cool, blue sea. This would be a hot ocean, perhaps tens of thousands of miles deep, resting on a solid core of rock and metal, with temperatures potentially reaching hundreds of degrees. In this strange, pressurized abyss, the very chemistry of life would operate under alien rules. Yet the most tantalizing clue came from a follow-up observation. In the atmospheric data, astronomers spotted a faint hint of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is almost exclusively produced by living organisms, particularly by phytoplankton in our oceans. It is a strong potential biosignature, a chemical shout that biology might be at work. In the deep, hot ocean of K218b, could some form of life be generating this compound? It is a breathtaking, unconfirmed possibility. The detection is not yet certain, and non-biological processes could potentially create it under such extreme conditions, but the mere suggestion transforms this mini Neptune from a scientific curiosity into a profound mystery. We are now forced to ask, could life begin and thrive not on a familiar rocky shore, but in a planetary ocean suspended beneath a crushing sky of hydrogen, where the sun never shines and the very water is scalding hot? The discovery of water vapor in the atmosphere of K218b did more than just surprise us. It created an entirely new category of potentially habitable worlds. Astronomers now call them Hycean planets, a name blending the words hydrogen and ocean. These are hot, water-covered worlds, significantly larger than Earth, enveloped in thick, hydrogen-rich atmospheres. Picture a planet where the sky is not blue, but a deep, hazy orange from the scattering of light through that dense gaseous blanket. Below that sky lies not continents, but a single planet-wide sea, so deep it could make our Mariana Trench seem like a puddle. The surface of this ocean would be hot, perhaps hundreds of degrees Fahrenheit, kept liquid not by moderate temperatures, but by the immense atmospheric pressure pressing down upon it. It is a vision of a steamy, dark, and profoundly alien aquatic universe. For decades, we dismissed such mini-Neptunes as sterile gas balls. The Hycean hypothesis turns that assumption on its head, proposing that within their global oceans, the chemistry for life could still begin. The hydrogen atmosphere acts as a powerful greenhouse trapping heat, but it also provides a blanket of protection from space radiation. Deep below the cloud tops, at the boundary where the hot ocean meets the rocky core, there could be environments not unlike the hydrothermal vents on Earth's seafloor. These are places where life on our planet may have first sparked, drawing energy not from sunlight but from chemical reactions between water and rock. On a Hycean world, such conditions could be the norm across an entire planet's hidden seafloor, a global network of warm, chemically rich nurseries. This single idea is a game changer. It means thousands of previously overlooked exoplanets, all those common mini-Neptunes we have been cataloging for years, must be re-evaluated. They are no longer just gas giants, they are potential ocean worlds. The search for life suddenly expands from a handful of rocky Earth twins to a vast new archipelago of steamy, deep-sea planets. The next step is to look for more than just water vapor in their skies. The James Webb Space Telescope is now hunting for other gases like methane and dimethyl sulfide, which in the right combinations could hint at biological activity stirring in those dark, hot seas. A confirmed biosignature from a Hycean world would tell us that life is not a delicate miracle confined to Earth-like conditions, but a robust, creative force that can take root in the most unexpected and extreme environments the galaxy has to offer. The search for a truly Earth-sized world in a peaceful neighborhood has a new champion. Orbiting a calm, quiet red dwarf star 100 light-years away, TOI 700d stands as a quiet testament to what might be possible. Discovered by NASA Transiting Exoplanet Survey Satellite, or TESS, this planet is almost exactly the size of Earth and sits perfectly within its star's habitable zone. What makes this world so compelling is not just its size or position, but the serene stability of its sun. Unlike the violent flares of Proxima Centauri, the star TOI 700 is a placid, older M-dwarf, offering its planets a gentle and consistent light. This stability is a gift of time, meaning any atmosphere or oceans are not being scoured away by stellar tantrums, giving life the precious eons it might need to begin and evolve. We know it is likely a rocky world with a solid surface upon which water could, in theory, pool and flow. But would it? To answer that, scientists have run sophisticated three-dimensional climate models, simulations that treat the planet as a dynamic globe with weather patterns, clouds, and oceans, not just a simple point in space. The results are promising. Under a wide range of plausible atmospheric conditions, the models suggest TOI 700d could indeed maintain stable regions of liquid water on its surface. It might be a world of vast, single oceans or scattered continents under a reddish sun, but the fundamental ingredient for life as we know it could be present. This combination of factors, its Earth-like size, its tranquil star, and its supportive climate models, makes it a perfect benchmark. It is a calibration point for the next generation of telescopes. When we finally train the most advanced instruments on its faint starlight, analyzing the subtle fingerprints of gases in its atmosphere, we will be looking at a world that represents one of our cleanest, simplest tests. A detection of water vapor or oxygen here would carry extraordinary weight because we have ruled out so many of the chaotic factors that complicate other discoveries. TOI 700d is not the most extreme or strange world on our list, but its profound normalcy might be the key that finally unlocks the door. The boundaries of a star's habitable zone are not fixed lines but soft and malleable borders. 31 light-years away, a super-Earth named JJ357d demonstrates just how far those borders can stretch. Orbiting a small, quiet M-dwarf star, this world receives roughly the same amount of stellar energy as Mars does from our Sun. On the surface of Mars, that energy is not enough to sustain liquid water without a significant greenhouse effect, leaving it a frozen desert. Yet JJ357d presents a fascinating possibility. What if it possesses exactly that, a thick, insulating atmosphere? With a dense blanket of gases like carbon dioxide or methane, this planet could trap enough of its star's faint heat to raise surface temperatures above freezing. This is the power of the greenhouse effect, not as a threat but as a planetary lifesaver. It acts like a cosmic quilt, holding warmth close to the surface and dramatically extending the outer edge of where liquid water can exist. This transforms our understanding of the habitable zone from a narrow band into a much broader region, where worlds once considered too cold might actually be temperate oases. The debate around JJ357d centers on this very question: how thick is its atmosphere and what is it made of? If it is a thin, wispy envelope like Mars, it is likely a frozen wasteland. But if it is a deep, dense shroud, it could be a world with sprawling ice caps, chilly oceans, and perhaps even simple life clinging to the warmth provided by its own sky. This super-Earth, nearly 6 times the mass of our own, would be a place of immense landscapes under a dim, red sun. Its higher gravity would sculpt lower, broader mountains and could help retain that crucial atmosphere over billions of years. It represents the far frontier of potential habitability, a world where life's chances hinge entirely on the composition of the air. Sometimes the most profound discoveries are not made by looking outward, but by looking back. Buried within the mountains of old data from the retired Kepler Space Telescope, a second look revealed a jewel we had almost missed, Kepler 1649c. This world is not a super-Earth or a mini-Neptune. It is a near-perfect Earth-sized twin, only about 6% larger than our own planet. It orbits a quiet red dwarf star roughly 300 light-years away, and it does so with a rhythm that feels hauntingly familiar, sitting squarely within the star's habitable zone. The sunlight that reaches its surface while tinted red carries about 75% of the energy that Earth receives from our Sun. This places its potential climate in a remarkably temperate range, not too hot and not too cold, but just right for liquid water to exist on a rocky surface. The excitement in the scientific community was palpable when this world was confirmed. It was not just another exoplanet, it was a validation. It proved that even in data we thought we had mined completely, gems of incredible value could still be hiding, waiting for a sharper eye or a better algorithm to reveal them. Kepler 1649c quickly earned its status as one of the most Earth-like planets ever found in terms of size and energy received. Its discovery tells a story of perseverance and second chances in astronomy. But what would it be like to stand on this world, under a crimson sky? The landscape might feel strangely recognizable. The gravity would be nearly identical to Earth, so walking would feel natural. The temperature, if it has an atmosphere similar to ours, could support vast oceans or continents with flowing rivers. The plants there, if they exist, might be black or deep purple to better absorb the redder wavelengths of light from their dim sun. Yet, like many red dwarf planets, it is likely tidally locked, with one face in perpetual daylight and the other in endless night. The most habitable region could be that eternal twilight belt, a band of perpetual sunrise and sunset circling the globe. This world is now a prime target for the next generation of telescopes. Its Earth-like profile makes it an ideal laboratory to search for biosignatures, those chemical signs of life. When we finally analyze the starlight filtering through its atmosphere, we will be conducting one of the most direct tests yet to see if a world so similar to our own in size and position also shares that most precious quality, a living biosphere. Wolf 1069b is a whisper from a nearby star, a world that feels almost within reach. Just 31 light-years away, this quiet red dwarf hosts a planet almost identical in mass to our own, nestled perfectly within its habitable zone. Its discovery in 2023 sent a ripple of excitement through the astronomy community, for it represents one of the closest known Earth mass worlds in a life-friendly orbit. The star itself is a gift, a calm and elderly red dwarf that does not erupt in the violent flares that plague so many of its kind, offering its planetary companion a stable and gentle light across the eons. This stability is crucial because Wolf 1069b is almost certainly tidally locked. One face of the planet stares eternally at its dim crimson sun, while the other is turned forever to the cold depths of space. For a long time, this was seen as a death sentence for habitability, creating a world of scorching desert on one side and a global glacier on the other. But modern climate models reveal a more hopeful picture. The key lies in the atmosphere. If this Earth twin possesses a reasonably dense atmosphere, winds and ocean currents could become planetary life support systems. Imagine vast atmospheric rivers carrying warmth from the blistering dayside across the Terminator line, releasing torrential rains in the eternal twilight zone. Ocean currents, if present, could perform a similar feat, circulating warmer water to heat the nightside's icy fringes. This constant churning of air and water could create a band of temperate climate encircling the entire planet, a ring of potential habitability where temperatures are just right for liquid water to pool and flow. The profound significance of Wolf 1069b is not just its Earth-like mass or its peaceful star, but its location. 31 light-years is, in cosmic terms, right next door. This proximity places it squarely on the shortlist for the most ambitious telescopes now being planned. Future instruments will attempt to directly image this world, not just detect its shadow, potentially capturing the faint blush of its atmosphere against the black of space. They will analyze its light for the chemical fingerprints of water vapor, carbon dioxide, or even signs of oxygen. Because it is so close and so similar in size to our own world, any discovery here would carry immense weight, offering a glimpse of what another Earth under a different sun might truly be like. It is a quiet neighbor with a potentially monumental secret waiting for us to look closer. Stability is a luxury in the cosmos, and Ross 128b is a world that seems to have secured it. Just 11 light-years from Earth, this temperate super-Earth orbits one of the quietest red dwarf stars ever observed. Unlike its turbulent neighbor Proxima Centauri, this star emits almost no dangerous flares, bathing its planet in a steady, gentle glow for billions of years. That profound calm changes everything. Without the constant barrage of sterilizing radiation and solar winds, Ross 128b has had the one thing life may need most: uninterrupted time. Its equilibrium temperature, a basic calculation based on its distance from its faint sun, suggests a climate that could be remarkably mild, potentially similar to Earth's in many regions. While we do not yet know if it has an atmosphere, the odds are strong that it is a rocky world with a solid surface, a blank canvas where the story of chemistry could have been playing out in peace. This stability is not just a minor advantage, it is the foundation upon which complex life might be built. On Earth, it took over 4 billion years of relatively stable conditions for single-celled organisms to evolve into the dazzling diversity we see today. A planet subjected to frequent global sterilization events would likely reset that clock again and again, perhaps never allowing life to progress beyond its simplest forms. Ross 128b, by contrast, offers the possibility of a deep, unbroken history. Imagine a world where evolution has proceeded without cosmic interruption, where life forms have had eons to adapt, specialize, and perhaps even develop intelligence, all under the constant, benign light of a sleepy red sun. The very quietness of its star makes this one of the most promising targets in our galactic backyard for detecting signs of a biosphere, as any atmospheric gases we find are more likely to be the product of a long-term, stable planetary process or even biology itself. The story of Gliese 581g is a scientific mystery that unfolded not in a telescope's eyepiece, but in the subtle mathematics of starlight. 20 light-years away, a quiet red dwarf star named Gliese 581 became the center of a fierce debate that captivated both astronomers and the public. Using a technique called the radial velocity method, scientists were searching for the star's telltale wobble. This method does not see a planet directly. Instead, it detects the tiny gravitational tug an orbiting world exerts on its star, causing the star to move in a minuscule, rhythmic dance. By measuring the shifts in the star's light, astronomers can infer the presence of planets, their masses, and their orbits. In 2010, a team announced they had found not just one wobble, but a pattern suggesting a remarkable world, Gliese 581g. The data indicated a rocky planet about 3 times the mass of Earth, orbiting squarely in the middle of the star's habitable zone. It was immediately hailed as the first truly Earth-like exoplanet found in the Goldilocks zone, not too hot and not too cold. The news ignited imaginations worldwide, but it also ignited a firestorm of scientific skepticism. Other researchers, looking at the same complex wobble data from Gliese 581, argued the signal for planet G was not strong enough to be distinguished from the natural noise of the star's own activity. They believed the pattern could be explained by a combination of the other known planets in the system and the star's magnetic cycles, a sort of celestial mirage. For years, papers were published for and against its existence, a back and forth that made Gliese 581g a ghost in the data, a world that might not be there at all. This controversy was more than just an academic dispute, it was a crucial stress test for our methods. It forced astronomers to refine their statistical models and confront the limits of detecting tiny, Earth-sized worlds with the radial velocity technique. The enduring public fascination with this possible world, however, speaks to a deeper longing. Gliese 581g became a symbol of hope and possibility, a placeholder for the idea that a perfect, habitable Earth twin was waiting to be confirmed. Even if it ultimately proves to be an illusion, its legacy is real. It pushed the technology and rigor of the search to new heights, ensuring that when we do finally confirm a world like it, we can be absolutely certain. The search for life often leads us to the dim, crimson glow of red dwarf stars, but we must not forget our own cosmic roots. Orbiting a star remarkably similar to our Sun, 42 light-years away in the constellation Pictor, HD 40307g offers a different kind of promise. This is a super-Earth, a world with a mass at least 7 times greater than our own, and it travels on a wide, leisurely path within its star's habitable zone. Its year lasts nearly 200 Earth days, a far more gradual rhythm than the frantic orbits of planets huddled close to red dwarfs. This distance from a brighter, sun-like star creates an environment with a familiar feel. The sunlight bathing this world would be a warm yellow-white, not the perpetual sunset hue of so many other candidates. The longer orbital period is a clue to a potentially more stable and complex climate. On Earth, our seasons are dictated by the tilt of our axis as we circle the Sun. On a world like HD 40307G, with a similar stellar parent and a longer orbit, seasonal cycles could be profound and drawn-out affairs. Imagine autumns that last for months, with slow, majestic changes in temperature and weather patterns, rather than the abrupt shifts forced by the gravitational tides of a close, small star. This super-Earth's greater mass, however, paints its potential landscape in bold, dramatic strokes. The surface gravity would be significantly stronger, perhaps more than double our own. This would sculpt a world of immense, low-lying mountain ranges and deep, vast valleys, as the very crust of the planet is pressed down under its own weight. The atmosphere would likely be thicker and denser, trapping heat efficiently and potentially creating a global greenhouse that keeps temperatures balmy even on the night side. For life, this presents a unique canvas. Biology here would need to be robust, built to withstand the constant heavy pull. Trees might grow incredibly strong and squat, while animals could evolve powerful, compact musculature. The thick air could carry sounds differently and make flight a challenging but potentially rewarding endeavor, possibly leading to creatures with immense, powerful wings. HD 40307G reminds us that a Sun-like star does not necessarily host an Earth-like twin. Instead, it can nurture a supercharged version of habitability, a world where the forces are more intense, the seasons are longer, and the very scale of life would be magnificently amplified. Kepler 22b was a gift of hope from the early days of the Great Planet Hunt. Announced in 2011, it was the Kepler Space Telescope's first confirmed planet orbiting comfortably within the habitable zone of a Sun-like star. The news felt like a revelation, a beacon in the dark proving that the strategy worked, that we could indeed find other worlds in that life-giving sweet spot. The star itself, a near twin to our Sun 600 light-years away, made the discovery feel profoundly familiar. Here was a star we understood, and around it, a world named Kepler 22b, about 2.4 times the size of Earth, basking in a glow of light very much like our own. The initial excitement was electric, sparking imaginations with visions of a blue and green world under a yellow sun. It represented a monumental shift, moving the question from whether such planets existed to how many we would find. In many ways, Kepler 22b paved the mental and scientific highway for the thousands of exoplanet discoveries that followed. It was the proof of concept that opened the floodgates. Yet, for all its symbolic importance, this world remains an enigma. That size, 2.4 times Earth's radius, places it squarely in a frustrating gap we call the Radius Valley. It is too large to be a typical rocky super-Earth, yet too small to be a standard gaseous mini-Neptune. So what is it? Scientists are still debating. It could be a rocky planet with a monstrous, dense iron core, a super-Earth with crushing gravity and perhaps a thin atmosphere. Or it could be an ocean world, a water-dominated globe with a deep, global sea enveloping a smaller rocky core, a precursor to the Hycean planets we would later theorize. It might even be a gaseous planet with a small, dense core and a surprisingly thick atmosphere for its size, a sort of transitional world. This fundamental uncertainty makes Kepler 22b a beautiful time capsule. It perfectly represents the early, thrilling, and messy days of exoplanet habitability science. We knew it was in the right place, but we had no idea what it actually was. The discovery taught us to temper our immediate visions of Earth twins with the hard reality of data, reminding us that a planet's location is just the first chapter of its story. The composition, the atmosphere, the very nature of its surface, these were mysteries that would require a new generation of tools to solve. Kepler 22b stands as a founding monument, a world that told us we were on the right path, even as it whispered that the path ahead was far more complex and wondrous than we had dared to dream. 12 light-years from Earth shines a star named Tau Ceti, a near twin to our Sun that has long been a beacon in our night sky and our science fiction. Orbiting this familiar star is a world that captures the razor's edge of habitability, a super-Earth known as Tau Ceti e. This planet, with a mass several times that of our own, circles perilously close to the inner boundary of its star's life-giving zone. The sunlight that falls upon it is intense and unwavering, a consequence of its tight, fast orbit. A year here passes in just 168 Earth days, a frantic sprint compared to our own leisurely journey around the Sun. This position makes Tau Ceti e a world of extremes, a place where the line between a temperate oasis and a hellish furnace is impossibly thin. With such proximity to its sun-like star, the planet is likely tidally locked, one hemisphere permanently facing the stellar fire. The climate models paint a stark picture. Without a reflective atmosphere to bounce away the intense heat, the dayside could be a scorching desert where lead would melt. Yet, if Tau Ceti e possesses a thick, cloud-shrouded atmosphere rich in water vapor, that same blanket could distribute heat around the planet, potentially creating more temperate conditions. This is the great debate: is it a super-Earth or is it a super-Venus? The answer lies in the composition of its air, a secret we are just beginning to unravel. The profound significance of Tau Ceti, however, extends far beyond this one tantalizing world. Astronomers have detected hints of at least 4 planets in this system, a miniature solar family orbiting a star so similar to our own. Finding multiple worlds here would be a cosmic mirror, suggesting that the architecture of our own home, with its several planets circling a yellow star, is not a rare fluke but a common blueprint in the galaxy. It raises the possibility of complex gravitational dances and perhaps multiple chances for life within a single stellar household. If Tau Ceti e itself proves too hot, its sibling, Tau Ceti f, orbits farther out in a cooler, more distant orbit, offering another candidate for habitability. This nearby, Sun-like star system represents a full test case, a complete laboratory for understanding how planetary families form and evolve around stars like our own. The data we gather from its light will tell us not just about one world, but about the very nature of solar systems we have yet to discover. While its sibling Tau Ceti e basks in intense heat, the outer world Tau Ceti f presents the opposite challenge. This super-Earth, orbiting farther from its sun-like star, dwells on the chilly outer fringe of the habitable zone. The sunlight reaching it is faint, only about a quarter of what Earth receives. On its own, that meager stellar warmth would likely leave the surface a global ice ball, a frozen sculpture locked in permanent winter. But planets are not passive objects. They have their own internal chemistry and atmospheres that can rewrite the rules of climate. For Tau Ceti f to host liquid water, it would need a powerful atmospheric ally, a thick blanket of greenhouse gases like carbon dioxide or methane. This insulating shroud would act like a planetary parka, trapping every precious bit of the star's weak heat and recycling it to warm the surface. It is a delicate balancing act: too much greenhouse gas and you get a runaway hothouse, too little and you have a permanent snowball. Finding that perfect equilibrium could transform this distant orbit into a cold but stable oasis. This creates a stunning cosmic contrast within a single family. Around the same familiar yellow star, we have 2 super-Earths representing the extreme boundaries of possibility. Tau Ceti e, hot and likely tidally locked, might be a cloud-shrouded pressure cooker or a scorching desert. Tau Ceti f, cold and distant, could be a frozen world or a temperate planet wrapped in a dense, warming atmosphere. They are sibling worlds on opposite ends of the temperature spectrum, each requiring a very specific atmospheric recipe to cross the threshold into habitability. The profound implication is that a single stellar system could host not just one, but two radically different types of habitable environments. Life on Tau Ceti E, if it exists, would have evolved under a blazing sun and crushing atmospheric pressures. Life on Tau Ceti F would be adapted to a dim light, long years, and perhaps a thicker, colder air. They would be alien to each other, products of the same star but forged in completely different crucibles. This nearby system teaches us that habitability is not a single condition, but a spectrum of possibilities, and sometimes that spectrum can exist right next door. The cosmic search for life is not a solitary hunt, but a survey of entire planetary families. Just 12 light-years away, a quiet red dwarf star named JJ1061 hosts its own compact family of at least 3 rocky worlds. Two of them, JJ1061c and D, offer a perfect lesson in how delicate the balance of habitability can be within a single stellar household. The inner planet, JJ1061c, orbits so close to its faint sun that its surface is almost certainly a scorched wasteland, receiving too much heat for liquid water to survive. It is a reminder of the inner frontier, a world where the habitable zone begins, not ends. But its sibling, JJ1061d, is a different story entirely. This super-Earth, with a mass a bit larger than our own planet, travels on a wider, slower path that places it squarely in the middle of the star's most conservative habitable zone. This is not the optimistic outer edge, but the sweet spot where climate models suggest a rocky world with a reasonable atmosphere could easily maintain liquid water on its surface. Its star's tranquil nature is another gift, meaning this potential haven has not been ravaged by stellar storms over the eons. The true significance of this discovery, however, lies in the pair of them together. Finding multiple rocky planets orbiting within or near the habitable zone of a single, quiet star is like finding multiple tickets in the same cosmic lottery drawing. It dramatically increases the statistical odds that at least one of those worlds has managed to get everything just right: the right atmosphere, the right geology, the right history of impacts to cross the threshold into a living state. In our own solar system, Earth and Mars both fell within the Sun's habitable zone early on, offering 2 chances for life to begin. JJ1061 presents a similar nearby experiment. While Planet C may be too hot and another outer planet may be too cold, Planet D sits in that Goldilocks position, a promising candidate in a system that proves rocky, Earth-sized worlds are not rare accidents, but common features around the most abundant stars in the galaxy. Deep in the constellation Lyra, 1,200 light-years away, a single star hosts a pair of worlds that could redefine our idea of an ocean. Kepler-62, a star cooler and smaller than our Sun, is orbited by 5 known planets, but 2 of them, Kepler-62e and Kepler-62f, stand out as a study in aquatic extremes. They are a duo of potential water worlds, each offering a different chapter in the story of a planet completely dominated by its seas. The inner world, Kepler-62e, is a warm super-Earth about 1.6 times the size of our planet. It orbits closer to its dim sun, and as a result, it is likely a world shrouded in thick, humid clouds and covered by a global, steaming ocean. The surface temperature here could be balmy, perhaps similar to a tropical Earth day, but with no land in sight. The sky would be a perpetual haze of water vapor, and the ocean below, warmed by its star and possibly by internal geothermal heat, could be thousands of miles deep. This is not a placid sea, but a dynamic, planet-wide weather engine, with storms of unimaginable scale circulating warmth from the equator to the poles. Life here would exist in a boundless aquatic realm, with ecosystems layered from the sunlit upper waters down into the eternal, pressurized dark. Its sibling, Kepler-62f, tells a colder tale. This smaller, rocky world orbits farther out, receiving only a fraction of the stellar energy. Without a substantial atmosphere, it is likely a frozen snowball, a marble of ice glinting in the faint starlight. Yet, this is where planetary science offers a spark of hope. If Kepler-62f has managed to hold onto a thick atmosphere rich in greenhouse gases, that very blanket could trap enough heat to thaw the ice and maintain a liquid ocean beneath an icy shell or even on its surface. It could be a world in transition with a slushy surface or a subsurface ocean like those we suspect exist on moons in our own solar system. Together, this pair illustrates the incredible diversity of water worlds that might fill the galaxy. They show us that a global ocean is not a single environment, but a spectrum, ranging from warm, steamy planets under cloudy skies to cold, icy worlds with hidden seas, each capable of brewing its own unique chemistry for life. Kepler 442b receives a gift of light almost identical to our own. Orbiting a calm orange dwarf star over 1,000 light-years away, this super-Earth basks in a stellar flux that is 97% of what Earth enjoys from the Sun. That number is astonishingly precise, meaning the amount of energy warming its potential atmosphere and surface is nearly a perfect match for home. Combined with its rocky composition and size, about 1/3 larger than Earth, this makes Kepler 442b one of the most Earth-like worlds we have ever catalogued in this fundamental way. But the true secret to its promise might not be the planet itself, but the nature of its sun. Orange K-dwarf stars represent a potential galactic sweet spot in the search for life. They are quieter and more stable than the flaring red M dwarfs, offering their planets a peaceful, consistent light without the deadly radiation storms. Yet they are also far more numerous and longer-lived than stars like our Sun. A K-dwarf can shine steadily for tens of billions of years, offering an unimaginable span of time for life to arise, evolve, and mature. Imagine a biosphere with 5 or 10 billion extra years of evolution compared to Earth. The complexity that could emerge in such deep time is beyond our comprehension. For a rocky world like Kepler 442b, this means the possibility of a stable, benevolent parent star that does not threaten to strip away its atmosphere, while providing the consistent energy needed for photosynthesis and climate stability over epochs. It is a world that gets the light just right under a star that promises to keep the lights on for a very, very long time. Proxima Centauri c is a lesson in cosmic extremes. Orbiting the same star as the promising Proxima b, this world could not be more different. It is a super-Earth or a small mini-Neptune, a massive world shrouded in mystery, traveling on a distant, frigid path far beyond the traditional habitable zone. A single year here lasts over 5 Earth years, and the feeble red light from its parent star provides almost no warmth. On the surface, temperatures would plunge to hundreds of degrees below zero, a realm where even the air would freeze solid. This seems like the very definition of a dead world, a frozen sentinel in the dark, yet its very distance and size invite us to think more creatively. What if life is not always a story written on a sunlit surface? Some scientists propose that Proxima c, if it has a rocky core beneath a thick, primordial atmosphere of hydrogen, could trap enough internal heat from its formation and from radioactive decay to create a surprising environment. That dense atmospheric blanket might act as an insulating cocoon, raising temperatures at the boundary with the solid core to levels far above the bitter cold of space. Even more intriguing is the possibility of a subsurface ocean. We see this model in our own solar system on Jupiter's moon Europa, a frozen ball of ice hiding a global, salty sea kept liquid by the gravitational tug of war with its giant planet. If Proxima c has a similar source of internal heating, perhaps from its own formation or from tidal forces, it too could harbor a hidden ocean beneath a crust of ice many miles thick. In that eternal, sunless darkness, warmed from below by geothermal vents, the chemistry for life could still begin, completely isolated from the frozen surface above. This distant neighbor forces us to expand the map of potential habitability far beyond the narrow band of starlight we once considered essential. Life may not need a sun at all, only a source of heat, liquid water, and time. Returning to the extraordinary TRAPPIST-1 system reveals another gem in its tightly packed family. TRAPPIST-1G is the sixth planet from its faint star, another rocky world that orbits within the system's broader habitable zone. While it receives slightly less stellar energy than its sibling TRAPPIST-1E, climate simulations present a captivating possibility. This world could be profoundly wet, a planet where water is not a scarce resource but the defining feature of the entire globe. The models suggest that with a suitable atmosphere, TRAPPIST-1G might be blanketed by a single, unbroken ocean, a world with no continents to break the waves under its deep red sun. The ocean's color in such light is a mystery, perhaps appearing black or a deep, murky violet, absorbing the faint crimson energy that manages to pierce the cloudy sky. Life in such an endless sea would never know the concept of land, its entire universe defined by currents, pressure, and the faint glow from above. Yet the true engine for life on this world might not be its star at all, but the relentless gravitational pull of its celestial neighbors. The 7 planets of TRAPPIST-1 are packed so closely that their gravitational fields constantly tug and squeeze one another as they orbit. This perpetual, rhythmic flexing generates heat deep within each world's core, a process known as tidal heating. For a water-rich planet like TRAPPIST-1G, this internal warmth could be transformative. It might prevent a global ocean from freezing solid all the way to the bottom, maintaining liquid water even at great depths. More importantly, this geothermal energy could fuel volcanic activity on the seafloor, creating hydrothermal vent systems. On Earth, such sunless, mineral-rich vents are oases of life, entire ecosystems that thrive on chemical energy rather than sunlight. On TRAPPIST-1G, tidal heating could sustain a global network of these biological havens, making its dark, deep ocean a teeming, warm sanctuary. This compact system teaches us that habitability can be a communal effort, where planets do not exist in isolation but actively shape each other's environments through an invisible dance of gravity, turning entire worlds into geologically active crucibles for life. The search for a true Earth twin demands a specific stellar environment, one that offers both stability and deep time. Far beyond the turbulent red dwarfs, the Kepler Space Telescope found a quiet candidate orbiting a star very much like our own. Kepler 1638b is a world almost identical in size to Earth, and it travels on an orbit that places it squarely within the habitable zone of a sun-like star. This combination is a rare and precious find in the cosmic census. While red dwarfs are far more numerous, their volatile nature and tidal locking pose significant challenges for long-term habitability. A sun-like star, however, provides a gentler, more consistent light and, crucially, a much longer lifespan. Our sun will shine steadily for roughly 10 billion years, giving life on Earth the immense span of time needed to evolve from simple cells to complex organisms. A planet like Kepler 1638b, circling a similar star, would receive that same gift of deep, stable time, a fundamental prerequisite for the slow, intricate dance of evolution that might lead to intelligence. The discovery of such a world tells us that the template for a long-lived Earth-like biosphere is not unique to our solar system. It exists elsewhere, a blueprint written in starlight and orbital mechanics. Yet, this promise comes with a significant hurdle for our scientists. Kepler 1638b is over 2,000 light-years away, an immense distance that makes detailed study extraordinarily difficult. Its star, while sun-like, is a faint point of light from our perspective. Detecting the subtle atmospheric signatures that would confirm habitability, let alone life, pushes our current telescopes to their absolute limits. For now, this world remains a statistical promise, a point of data proving that planets of our size, in our position around our kind of star, are out there. It is a beacon in the data, a reminder that while the most easily studied planets may orbit small, red stars, the most familiar and potentially stable homes for life still circle suns like our own, waiting patiently in the distance for our technology to catch up to their silent, ancient light. A year on Kepler 1544b unfolds with a slow, majestic patience. This super-Earth, orbiting a star very much like our own, completes a single journey around its sun, not in 365 days, but in 168. That extended orbit places it firmly within the habitable zone, but it also rewrites the fundamental calendar of life. On Earth, our seasons are a product of our tilted axis as we make our annual circuit. Kepler 1544b, with its much longer path, introduces the possibility of seasons drawn out over months, even years. If this world is tilted like our own, the result would not be a quick transition from spring to summer, but a prolonged, gradual immersion. Imagine a summer that lasts for 40 Earth days or more, where the sun climbs slowly to a zenith and lingers there, baking the landscape under a steady, familiar glow. This would be followed by an autumn just as long, a slow, creeping coolness that allows ecosystems ample time to prepare for a winter of profound and extended darkness. For any life there, time itself would feel different. Biological rhythms would sync to this grand, slow metronome. Plants might have growing seasons that span multiple Earth years, developing deep, extensive root systems to survive the long winter dormancy. Animals could evolve life cycles and migration patterns measured in these long planetary years, perhaps hibernating for Earth decades at a time to conserve energy through the deep cold. The very pace of evolution could be altered, with generations turning over more slowly under the influence of this drawn-out celestial clock. This world challenges our Earth-centric view of time. It shows us that a stable, sun-like star does not guarantee a familiar rhythm. Habitability can wear many faces, and on Kepler 1544b, the face of life would be one of profound patience, adapted not to the quick pulse of a short orbit, but to the slow, deep breath of a long year. But the hunt for these quiet, long-lived worlds has a new champion. The Speculus project, a network of robotic telescopes designed to stare at the dimmest stars in the sky, recently delivered a stunning find. Orbiting a faint, ultra-cool dwarf star about 100 light-years away is a super-Earth named LP899c, also known as Speculus 2c. This world, about 40% larger than our own, is a rocky giant perfectly positioned in the very center of its star's habitable zone. Its discovery is a masterclass in modern astronomy strategy because every element of this system is optimized for one thing, answering the ultimate question. The star itself is so small and cool that the planet blocks a significant fraction of its light each time it passes in front, making the transit signal exceptionally clear and strong. Furthermore, because the star is so faint and inactive, it provides a dark, steady backdrop against which to study the planet's atmosphere. There is no stellar noise to confuse the delicate measurements. This makes LP899c not just another candidate, but arguably the most promising target we have for the James Webb Space Telescope to search for an atmosphere on a temperate, Earth-sized world. When Webb turns its instruments toward this distant system, it will analyze the starlight that filters through the planet's thin, hazy rim. Scientists will be looking for the chemical fingerprints of water vapor, carbon dioxide, methane, or even oxygen. A detection here would be a landmark, providing our first detailed chemical map of the air around a world that could host life. This planet represents the next generation of the search, where we move beyond simply finding planets in the right place to meticulously probing their environments, one molecule at a time. A planet's density can whisper the secret of its composition. 100 light-years away, orbiting a binary star system in the constellation Draco, the world TOI 1452b tells a story of profound, silent depth. Measurements of its size and mass reveal a planet less dense than a rocky world like Earth, but denser than a gaseous mini-Neptune. The most elegant explanation is that this super-Earth is not a ball of rock and metal, but a globe of water. Scientists estimate it could be up to 30% water by mass, a staggering figure when you consider Earth, the blue marble, is only about 1% water by mass. This is not a world with oceans, it is an ocean that has become a world. Imagine a planet with no continents, no mountains breaking the surface, no beaches or shores of any kind. From pole to pole, the view would be an endless, rolling expanse of water under a sky lit by two faint suns. The ocean itself would be an alien abyss, not hundreds of feet deep like our own seas, but hundreds of miles deep. At such immense pressures, the water at the very bottom would be forced into exotic forms of ice, not from cold but from sheer weight, creating a solid floor of hot ice Roman 7 beneath the liquid sea. This is a planetary aquarium on a scale we can barely comprehend. In such an environment, life would have a universe of liquid to explore, but no solid ground to ever call home. Evolution here would follow a path of pure aquatic specialization. Near the surface, where starlight from the binary suns could penetrate, vast floating forests of photosynthetic organisms might drift on the currents, forming the base of a complex food web. Deeper down, in the eternal twilight and then the permanent dark, life would have to find other sources of energy. The entire seafloor, that strange hot ice boundary, could be lined with hydrothermal vents spewing mineral-rich fluids and warmth from the planet's interior. These would be oases of chemical energy, supporting entire ecosystems of creatures unlike anything on Earth, perhaps glowing in the dark or sensing their world through pressure changes and subtle electrical fields. Intelligent life in such a realm would have no concept of fire, of building with stone or wood, or of looking up at a night sky unobstructed by a watery ceiling. Their entire civilization, their art, their science would be born from the dynamics of fluids, the mysteries of the deep pressure, and the faint, filtered light from above. TOI 1452b is a reminder that a living planet does not need familiar geography. It only needs a stable medium where chemistry can dance, and in this world, that medium is an ocean that never ends. A world's promise can be shattered by the fury of its own sun. Kepler 438b was once celebrated as a triumph, an Earth-sized world orbiting comfortably in the habitable zone of a distant red dwarf. On paper, it was everything we hoped for, a rocky twin basking in the right amount of starlight for liquid water. For a brief, exciting moment, it ranked among the most Earth-like planets ever discovered. But the story of habitability is written in more than just size and distance. It is also written in the violent history of stellar tantrums. The star Kepler 438 is not a calm, quiet neighbor like Teegarden star or Ross 128. Instead, it is a tempest. Observations revealed that this star unleashes catastrophic superflares, eruptions of energy so powerful they dwarf anything in our sun's history. These are not mere solar flares, they are apocalyptic events. A single superflare from Kepler 438 could release the energy of 100 billion megatons of TNT, enough to bathe its orbiting planet in a torrent of X-rays and ultraviolet radiation thousands of times more intense than Earth ever receives. For a world like Kepler 438b, the consequence is almost certainly a death sentence. Such repeated, violent blasts would have acted like a cosmic sandblaster, relentlessly stripping away any protective atmosphere the planet might have once possessed. Imagine a planet with a beautiful, thick blanket of air, slowly and utterly shredded over millions of years, its gases ionized and blown out into the void of space by the relentless stellar wind following each flare. What remains today is likely a barren, airless rock, its surface directly exposed to the harsh vacuum and radiation, all traces of its once promising oceans long since boiled away and lost. This discovery delivered a crucial, sobering lesson in our search. It taught us that a planet's address is not enough. A quiet star is not a luxury. It is a fundamental requirement for long-term habitability. A world can be the perfect size, in the perfect orbit, with the perfect ingredients, but if its sun is a violent toddler prone to cosmic tantrums, any chance for a stable biosphere is likely erased before it even begins. Kepler 438b stands as a ghost of potential, a cautionary monument reminding us that the search for life is a search for peace, for stellar neighborhoods where the lights stay on steadily and the sky does not periodically catch fire. JJ1214b is a world cloaked in mystery. For years, this iconic mini-Neptune has been a cosmic riddle, a planet that refuses to reveal its true nature. Orbiting a red dwarf star 48 light-years away, it is larger than Earth but smaller than Neptune, a size that places it in a frustrating and fascinating category all its own. The central question is deceptively simple: what lies beneath its sky? Our telescopes have spent years trying to pierce its thick global shroud, a uniform, featureless haze that stubbornly blocks our view. This persistent veil means we cannot see if there is a solid, rocky surface down below, or if the atmosphere simply grows denser and denser until it merges with a global, superheated ocean. It is the ultimate planetary poker face, giving away nothing. This very obscurity makes it a perfect symbol for the vast unknown in exoplanet science. We have catalogued thousands of worlds, but for so many of them, their deepest secrets, the composition of their surfaces and interiors, remain locked away. JJ1214b represents that frontier of ignorance, a reminder that for every clear-cut rocky super-Earth we find, there may be a dozen worlds like this, enigmatic and defying our easy labels. Yet within that mystery lies breathtaking potential. If the haze hides a deep, hot water ocean, then JJ1214b could be a steamy Hycean world, a place where life might brew in the dark depths under immense pressure. If it has a solid core, that core might be unlike any rock we know, forged under conditions impossible in our own solar system. This planet forces us to confront the thrilling possibility that the galaxy is filled with entirely new classes of habitable environments, architectures for a world that our Earth-bound imaginations have not yet conceived. The search does not end with finding a planet in the right place. It begins with unraveling what that planet truly is, and JJ1214b stands as a silent sentinel at that border, guarding the secrets of the forms a living world might take. From scorching lava planets to frozen snowballs, from Earth's familiar cousins to the steamy, deep-sea abysses of Hycean giants, our journey has revealed a cosmos teeming with possibility. Each of these 30 worlds tells a different story of what a living planet could be. They are not copies of Earth, but a breathtaking gallery of alternatives, proving that the conditions for life are not a single, fragile recipe, but a vast and creative menu. The unifying truth is clear and profound. The galaxy is not a barren desert. It is a neighborhood filled with potential homes, each with its own unique sky, its own rhythm of seasons, and its own hidden chemistry waiting to stir. Our map of these worlds is still being drawn, with every new observation from telescopes like the James Webb adding a new landmark, a new mystery to solve. The search is accelerating, and the greatest discoveries likely still lie ahead, hidden in the faint light of a distant star. So keep looking up and keep wondering. Follow each new announcement, each whispered signal from the data, because out there among the countless stars, another world is waiting to be found, and with it, the answer to our oldest and most beautiful question: are we alone?